Imagine you spill a cup of coffee on your kitchen floor.
Oh, yeah.
The worst.
Right. You see the puddle, and you immediately know to walk carefully around it because, well, you instinctively understand that liquid on a smooth surface makes it slippery. You understand friction.
Exactly. You have a mental model of how the physical world actually works.
But if you have, like, a state-of-the-art, multi-million-dollar AI robot in your house, it might just walk right into that puddle and crash to the floor.
Oh, it almost certainly would.
Why? Because even though it's memorized millions of images of dry floors and perfectly calculated its joint angles, it actually has absolutely no idea what friction is. It doesn't understand the rules of physics. It just mimics patterns.
Right. And that fundamental limitation is exactly what's holding back the entire next generation of artificial intelligence. I mean, we've built machines that are incredibly sophisticated at predicting the future based on the past, but they're utterly incapable of explaining why things actually happen, which is wild when you think about it. But welcome back to another deep dive. Today we are exploring a breakthrough that aims to finally teach machines the underlying laws of reality.
It's a big one.
It really is. Our mission today focuses on a deeply fascinating 2026 state-of-the-art paper. It was submitted to the ACM by Yi Yu from Hiroshima University and Tetsunari Inamura from Tamagawa University. The title is quite a mouthful. It's called Self-Evolving Cognitive Framework via Causal World Modeling for Embodied Scientific Intelligence.
Yeah, they really they went for it with that title.
They really did. So, okay, let's unpack this, because if we look past that dense academic title, the core premise is absolutely revolutionary. We're talking about a framework that forces embodied AI, robots operating in the messy physical world to stop acting like giant prediction engines and start acting like actual scientists.
That is honestly the perfect way to frame it. The authors are asking this really profound question. What if we gave a robot the ability to form hypotheses, conduct physical experiments, and independently discover the hidden rules of its environment?
Instead of us just feeding it rules.
Exactly. What if it learned by actively questioning the world, rather than just regurgitating massive data sets?
To really appreciate how massive of a leap this is, I feel like we need to understand the trap that current AI systems are stuck in right now.
Yeah, absolutely. The predictive trap.
Right, because right now, the industry darling is the VLA model, right? The vision language action model.
Mm-hmm.
You talk to a robot, it sees its environment, it crunches a billion parameters, and it outputs the most statistically probable next movement. And they look so capable. But this paper aggressively argues that relying on predictive modeling is a complete dead end for true general intelligence.
It is a dead end. Because predictive models, well, they capture correlations, not causal mechanisms.
Mm-hmm.
Current systems are brilliant at finding statistical regularities, right?
Mm-hmm.
They know that event A frequently precedes event B.
Like they know that when a hand closes around a mug, the mug usually rises up.
Yes. But they don't actually know that the hand causes the mug to rise. They don't understand gravity or grip strength or mass. And this becomes a massive catastrophic problem when the environment shifts. It's what researchers call out-of-distribution scenarios.
That brings me back to the spilled coffee. Or think of a human driver who has only ever driven on perfectly dry roads.
Oh, that's a good analogy.
They've memorized the exact sequence of steering wheel movements to get from point A to point B. But the moment it rains, they crash. Because they don't fundamentally understand why the car slips. They don't understand the causal mechanism of tire tread on water.
They just know the rote pattern of dry weather driving.
Exactly.
And that is the correlation versus causation problem in a nutshell. The paper highlights three major interconnected flaws with current AI systems. First, as we just discussed, they capture observational regularities instead of causal mechanisms. Second, even the rare models that try to incorporate causality usually assume a completely fixed causal structure. They're rigid. They can't dynamically revise their understanding of the world's rules on the fly if reality suddenly surprises them.
Which it always does.
Always. And third, the way they handle continual learning is fundamentally flawed.
Wait, I actually want to push back on that last point for a second.
Sure.
Because hasn't the industry largely solved this continual learning problem? I mean, we constantly hear about foundation models getting updates, ingesting more interaction data, and using techniques to not forget old tasks. It seems like throwing more data at the problem actually works.
Well, what's fascinating here is how the paper completely redefines what true continual learning actually requires.
Hmm.
Yes, feeding a model more data helps it adjust its internal parameters to avoid something called catastrophic forgetting.
Which is just when learning a new task accidentally overwrites the memory of an old one, right?
Exactly. But all that does is parameter adaptation. The AI isn't refining its internal causal logic at all. It's just finding a new, slightly broader statistical compromise that fits the expanded dataset.
Oh, I see.
Like the robot memorizes 10,000 ways to hold 10,000 different cups, but it still doesn't know that gravity pulls things down. More data fixes the parameters, but it completely ignores the underlying mechanism of how the machine thinks the world actually works.
Okay, that makes sense. I get why just predicting the next frame of a video or dumping more data into a model is a dead end. But if we actually want them to learn cause and effect, they have to interact with the world differently. Like, how do you mathematically teach a machine the concept of cause and effect?
That brings us to the beating heart of this paper, the SCM, or the structural causal model.
Right. The math in this section is elegant, but, for anyone who hasn't stared at a causal graph lately, it can be a little intimidating.
It's a lot of symbols.
Let's break down the foundational equation they use to define a causal world model. It's written as M equals the tuple of U, V, F sub theta, and P sub theta of U. Let's translate that into plain English.
Yeah, let's strip away the jargon. In this equation, M is the complete causal world model. Basically, the robot's internal brain map of reality.
Okay.
V represents the endogenous variables. These are all the visible, measurable things the robot can see and interact with. The position of its own arm, the state of the room, the objects on a table.
The stuff it can actually perceive.
Right. Then F sub theta are the structural equations. You can think of these as the actual hidden rules of physics that dictate how all those visible variables in V interact with each other.
And the really crucial part is U, right? Because U is the exogenous noise. It's all the unobserved, random stuff in the universe that influences the environment but can't be perfectly controlled.
Precisely. The universe is messy. And the absolute brilliance of this specific SCM framework is how it splits that random noise, U, into two distinct parts.
This is the genius part.
It really is. It splits it into state transition noise, which they call U sub S, and observation noise, which is U sub O.
Okay, here's where it gets really interesting. Because the difference between those two types of noise changes everything about how the robot processes reality. I was thinking about it like this. Imagine you're walking into a room and you can't see the furniture clearly.
Okay, I'm with you.
State transition noise, that U sub S factor, is like the room being filled with thick, heavy fog. The environment itself is stochastic, it's messy, it's objectively hard to see through. Noise is out there in the world.
Right.
But observation noise, that U sub O factor, is like walking into a perfectly clear, brightly lit room, but you have heavily smudged fingerprints all over your own glasses. The environment is completely fine, but your sensors are flawed.
That is a brilliant way to visualize it. By mathematically separating environmental randomness from sensor failure, you give the robot a principled foundation to test reality.
It knows whether the world is being unpredictable or if it just needs to doubt its own cameras.
Exactly. And the way it tests that reality is by treating its own physical actions differently. In a standard predictive model, an action is just the next physical step in a program sequence. But in this causal framework, an action is modeled mathematically as a deliberate causal intervention.
They use a specific notation for this, right? The do
Yeah.
operator.
They write it as do, and then in parentheses, a sub-T.
So the robot is essentially declaring, I am not just moving my arm because the statistics told me to, I am going to intentionally do this specific action at this exact time, specifically to see how the universe responds.
Exactly. This creates what the authors call intervention awareness. When the agent applies that do operator, it mathematically isolates the causal effects of its own actions from all those random environmental confounding factors.
The fog in the room, so to speak.
Yes, the fog. It allows the robot to distinguish between the cup fell because the table shook randomly and the cup fell because I actively pushed it. It is actively querying the environment to reveal those hidden structural rules, the F sub theta we talked about.
Which is exactly what a scientist does in a lab. You control the variables, you perform an intervention, and you measure the outcome.
Exactly.
But making a physical intervention is only half the battle. If a robot drops a cup and it shatters, how does it process those results? How does this system actually update its own brain when reality violently contradicts its expectations?
This leads us directly to the core engine of the framework, the self-evolving refinement loop. The paper outlines a 5-step cognitive process governed by a mathematical function they call the structural evolution operator.
Denoted by the Greek letter phi, right?
That's the one. But rather than just, listing the steps, let's look at how this flows as a continuous narrative of learning.
Okay, let's say the robot tries to pick up a wet glass, and it slips right through its robotic fingers and shatters on the floor. In a traditional system, that's just an error to be minimized on the next run.
A negative reward.
Right. But here, the first thing the robot does is self-observation. It logs its interaction history, its intention, its action, and the messy result. But then, instead of just logging a statistical error, it actively diagnoses the failure.
Right, that failure attribution is the pivot point. The framework treats the dropped glass not as a mistake, but as an implicit diagnostic intervention. The anomaly tells the system, hey, your internal explanation of the world is fundamentally broken.
It realizes its internal map of reality missed a crucial variable, in this case, the moisture on the glass.
Which forces it to play detective. It initiates causal discovery. The robot attempts to uncover the latent causal mechanisms it missed, trying to refine its internal structure based on the data of the failure. And this leads to what I think is the most mind-bending part of the paper.
Counterfactual reasoning.
Yes. The robot essentially pauses and asks itself, okay, what would have happened if I had done action, a prime leg gripping 10% tighter instead of my actual action A?
And it does this using equations 9 and 10 from the paper, simulating that hypothetical outcome using its current inference time parameters, which they denote as theta prime.
Yep.
And just to clarify, inference time parameters is really just a highly technical way of saying the rules of physics exactly as the robot understands them in that exact millisecond, right?
Exactly. It uses its current best guess of how the world works to simulate an alternate reality where it acted differently.
Okay, I have to jump in here with a major pushback.
Go for it.
I understand a robot physically trying something, failing, and learning from the broken glass in the real world. But if the robot is simulating these what-if scenarios entirely inside its own head, how does it ensure it's not just hallucinating false realities?
It's a huge risk.
Right. We see large language models hallucinate confident nonsense all the time. If this robot is just daydreaming alternate timelines based on flawed parameters, isn't it going to learn entirely wrong lessons about physics?
That is the exact vulnerability the authors anticipate. If left unchecked, the robot would absolutely just reinforce its own delusions. So they solve it mathematically with a crucial metric called causal discrepancy, denoted as delta sub t.
Okay.
This measurement acts as an anchor to reality. It forces the system's internal imagination to strictly align with factual environmental feedback. When the robot simulates a counterfactual, it is tightly constrained by the structural equations it has already physically validated in reality.
Oh, I see.
So if its internal simulation contradicts the hard data of its physical experiments, the causal discrepancy metric spikes.
And when that discrepancy spikes, it triggers the structural evolution operator, phi, to aggressively revise the hypothesis. It forces the robot to update its internal causal structure, its parameters, and its estimation of uncertainty.
Yes, it essentially rewires its own cognitive framework to eliminate the hallucination.
That is wild.
And because it is revising the actual rules of the environment, rather than just memorizing a specific sequence of actions to pick up one specific cup, it achieves what the authors call mechanism-level generalization.
Meaning it can transfer that knowledge literally anywhere. Like, if a robot learns the causal mechanism of friction by slipping on a wet floor, it doesn't just know how to walk on that one specific floor. It understands the concept of friction.
Broadly applicable.
Right. You could take its digital brain, drop it into a completely different robot body with different metallic legs in a different building on the other side of the world, and it would still fundamentally understand that liquid plus a smooth surface equals a loss of traction.
It abstracts the causal mechanism entirely away from the observational noise.
Okay, but if these AI agents are running these internal self-correcting simulations to test hypotheses, it creates a massive problem for us humans.
How so?
Well, how do we even know if they are getting smarter? Because clearly we aren't just talking about a machine that can flip burgers or sort boxes anymore.
Oh, totally. We need a completely new vocabulary for robotic intelligence. And the paper actually introduces a graduation system for this new era, breaking it down into 4 interconnected levels of embodied scientific intelligence.
The lowest level is execution. That's just interacting with the environment, following the recipe, doing the tasks.
Right. But then you graduate to the second level, Inference.
Hmm.
This is where the agent can actually interpret its observations and offer a causal explanation for why the environment responded the way it did.
It can explain why the cup fell.
Exactly.
Hmm.
Then the third level is where it gets really wild. Design.
Design.
Yeah, meaning the agent can autonomously formulate intervention strategies.
Mhm.
It designs its own physical and simulated experiments to aggressively test its hypotheses.
Wow. And the final level is discovery. The ability to identify entirely novel causal structures in the world through this continuous iterative loop of experimentation and model refinement.
And to achieve these higher levels of design and discovery, the framework relies heavily on that simulated experience we just discussed, the counterfactual daydreams. But the paper dissects simulation across three very specific dimensions that dictate how useful those daydreams actually are.
Fidelity, counterfactuality, and agency.
Exactly.
Agency is its ability to actively drive the simulation rather than just watching it like a movie. Counterfactuality is the ability to test branching what-if paths. But I want to zero in on that first dimension, fidelity.
Okay.
Because when I think of computer simulations, my brain immediately assumes that maximum realism is always the ultimate goal.
That's what we usually strive for, yeah.
Right. If you are simulating reality, shouldn't you want a 4K, hyper-realistic, physics-perfect simulation? Why would an agent ever benefit from a low-fidelity simulation?
It seems totally backwards, right?
Oh.
But lower fidelity simulations are actually incredibly valuable for achieving that mechanism level abstraction we talked about. High fidelity often means high noise.
Oh, I see where this is going.
If you perfectly simulate every microscopic texture, every subtle lighting change, and every tiny breeze in a room, you might completely obscure the underlying mechanics. Think about how a human physicist works.
Oh, this makes me think of the classic physics joke, assuming a spherical cow in a vacuum.
Exactly. That is the perfect example. When a physicist wants to calculate the basic trajectory of a falling object, they intentionally ignore air resistance. They strip away the messy, high-fidelity real world to isolate the true, fundamental causal structure of gravity.
You make the simulation less realistic to make the underlying rule more visible.
Precisely. This embodied AI does the exact same thing. By selectively reducing the fidelity of its internal simulation, it strips away the observational noise to ensure its hypothesis about the underlying structural equation is actually found.
It simplifies the chaos to see the skeleton of reality.
That's a great way to put it.
But if these AI agents are essentially acting like scientists performing peer-reviewed research in their own simulated minds, isolating variables and discovering the laws of physics, our old tests for robotic intelligence are completely obsolete. We can't use the old benchmarks because those just grade physical tasks, not actual comprehension.
You certainly don't use the old benchmarks, no,
Yeah.
which were almost entirely based on task completion rates or trajectory imitation. Like, did the robot pick up the apple? Yes or no? Did it perfectly copy the human's arm movement? Yes or no?
Right, completely binary.
The authors argue those metrics are totally dead. To evaluate a scientist, you have to test their causal understanding. So they propose a totally new, intervention-driven benchmarking paradigm.
The paper lists 6 specific new benchmarks to replace the old ones. Let's look at a few of the most important ones. First is causal intervention robustness. Basically, can the AI maintain its performance when you structurally manipulate its actions in unexpected ways? Second is counterfactual accuracy. When we compare the robot's simulated what-if scenario to a parallel ground truth simulation, how close is its imagination to reality?
And the third one is critical: failure utilization. This doesn't just measure if the robot eventually succeeds, it mathematically quantifies exactly how well an agent turns a mistake into structural knowledge.
That's a huge shift.
It is. In traditional reinforcement learning, a failure just means the robot gets a negative reward and tries something slightly different. Under this new benchmark, we measure if the robot actually restructures its internal causal graph after a failure.
Then there is long-horizon causal consistency. Over a long period of self-updating, does the model logically drift into nonsense, or does it preserve its invariant rules?
Right. Does it stay sane?
Exactly. Fifth is self-modification stability. When it updates its own code, does it become smarter, or does it accidentally destabilize its entire causal structure and break its own brain?
Always a risk when you're rewriting your own logic.
And finally, cross-platform transfer robustness. Like you mentioned earlier, can it take its causal knowledge of friction and apply it in a totally different robotic body?
But, even with these rigorous new benchmarks, the paper acknowledges we aren't at the finish line yet. There are major remaining challenges for this framework to operate safely and effectively in the real, messy world. One of the absolute biggest hurdles they mentioned is multi-agent causal attribution.
So what does this all mean for you listening right now? Let's bring this into your home. Imagine you have one of these advanced embodied AI systems in your kitchen. You are trying to open a stuck cabinet door, and the robot realizes you need help.
Okay, setting the scene.
You both reach for the handle and pull at the exact same time, and the door violently pops open. Multi-agent causal attribution is the robot's ability to figure out the truth in a shared environment. Did the door open because you pulled it? Because the robot pulled it? Because of your combined force? Or because of some unobserved factor like the humidity dropping in the kitchen causing the wood to shrink?
If we connect this to the bigger picture, untangling that kitchen scenario shows why this represents the ultimate paradigm shift in artificial intelligence. When an AI can correctly attribute cause and effect in a dynamic, shared environment with human beings, it will have officially crossed the threshold from predictive intelligence to epistemic intelligence.
Epistemology being the study of knowledge itself, how we know what we know.
Exactly. These machines will no longer just be statistically guessing the future based on the past. They will be actively constructing, testing, and understanding the generative causal structures of our shared reality. They are learning how to know.
They graduate from being statistical mimics to actual students of the physical universe.
Beautifully said.
And that brings me to a final thought I want to leave you with today. We've talked deeply about how these self-evolving agents rely on generating endless what-if alternate realities to refine their understanding of our world. They are constantly running high-agency, counterfactual simulations to test their structural hypotheses.
Millions of them.
Millions. So if their entire cognitive process requires building and testing thousands of alternate timelines for every single action they take, at what point does the vast library of their simulated, causally consistent universes become infinitely more complex, rich, and varied than the single physical reality they actually inhabit alongside us?
Wow. That is a wild thought.
It's something profound to chew on as we watch the generative AI frontier move off our screens and into the physical space around us. Thank you for joining us for another deep dive, and as always, keep questioning the world around you.